For those of you returning online, I apologize. I hit spacebar. I thought I was at the PowerPoint, but it stopped the stream. Okay, so we have this equation then. Essentially, the BOD in our mixture is the BOD of the wastewater times that volume and the BOD of the dilution water times that volume. So very straightforward there. What we can do with that is rearrange and solve in terms of P, which was our dilution factor, which was the volume of the sample divided by the volume total. Maybe we write it as V wastewater, since normally we're testing BOD for wastewater. Really, we could do it for any sort of sample. It could be a pond water, could be whatever, but most often when we're talking about BOD, it's in the context of wastewater. Okay, so we can rearrange, and I'm not going to go through all the derivation. I think maybe I mentioned this last time, but essentially you can rearrange. So P here, we have this definition, and if you go through some algebra, you can say 1 minus P then is equal to the volume of dilution divided by the volume of mixture. So it's a little bit of fractional analysis, simplification sort of thing. You can apply that to this and then solve for BOD wastewater, and you get this form, which then simplifies into this final equation, which you'll be given. Okay, so with that, that's something we can use to solve for a BOD of a sample or of a target, even if we dilute some water. So that's going to require the two experiments. Like I mentioned, we'll have one volume that has volume of the dilution water plus the volume of the sample, and the other one will be completely filled with dilution water. And we're going to test the oxygen drop in both cases, and that's going to give us the information required, where we have dissolved oxygen initial and dissolved oxygen final. Actually, I think the book I was using wrote I instead of not there, so DOI. And then for the dilution water, we just separate the terms to say BI and BF to be the initial and final in that particular vial. So that's just the definition there. So that would be the DO initial in dilution water. And of course that would be DO final. Okay, so that gives us a handy expression. So let's use it. Here we have a test bottle containing aceted dilution water has its DO level drop by 1 milligram per liter in a 5-day test. And separately, a 300 milliliter BOD bottle filled with 15 milliliters of wastewater, with the rest seeded. The rest is seeded dilution water, and you can express that as a 1 to 20 dilution. And that one experiences a drop of 7.2 milligrams per liter in the same time period. So the question is, what would be the 5-day BOD of the waste? So take a couple minutes and work on that. Given the information there. No, the final, well, the final is going to be according to the final exam schedule, which I'll have to check. That sounds right. Yeah, I have it in our syllabus as December 8th, Wednesday, 12:30 to 2:30. Okay. Okay, so for this problem, first of all, you had P given as a ratio 1 to 20, so that you probably ought to recognize that's 1 divided by 20, or you just do the 15 divided by 30. And when you do that, that's essentially 0.05. And then you can do 1 minus that, so 1 minus P is 0.95. So that gives you a couple of the values you're going to need. And then the solved oxygen initial minus final for the sample case and the dilution case, you don't have any values given for the saturation or initial or even the final. What you're given is a drop. And so given that, it doesn't really matter where you started or where you ended with. You can just insert into these components the drop, right? Because it's kind of the same thing really. Is this is how much it dropped for the mixture case, and this is how much dropped in the dilution water only case. So you can put these numbers in: 7.2 milligrams per liter drop minus the 1 milligram times that 0.95, divide all that by 0.05, and if I remember correctly, this is 125 milligrams per liter. That's the answer. Yeah.
It's the DO case, is that kind of like the control group, or like how do you know which set of numbers was the 7.2 and which was the
Okay.
1? Like which words that set you off?
Good question. So for those online, the question is, how did I know which set here out of the two how did I know which one was 7.2 versus 1? And the answer is actually from that where we were deriving the equation earlier. That BOD in the mixture is on the left here minus the BOD in the dilution. So really this value down here, the D versus the M. And when we measure the BOD, when we write it out this way, what we're saying is we measured that BOD and found it to be something, right? And in that mixture case, the way to measure it and report it is what was the DO initial minus the DO final. So this one's going to be for the mixture, and this one is going to be for the dilution. Does that make sense?
Yeah, I see. I thought those were like 2 separate things, but I see how they line.
Yeah. Okay. So and that's a good point there. These two equations are the same. I just reworded it, changing that right there. And this actually is a really nice point to highlight here. You could, like, the whole reason we're doing any of this is because if we were to try to write out the BOD of the wastewater itself, it would have to be like 120 minus to have it a big enough drop, the drop itself, you'd have to start at 120 and go down to 5 to get our 115, or excuse me, 130. So in order to be able to measure this properly, you'd have to have something like 130 minus 5. You start with 130 milligrams per liter and you end up with 5 milligrams per liter. But that's unrealistic because we can't have that much oxygen in water. So the whole reason we're doing all of this dilution nonsense and the seed water and all of that is because that's just not practical. We just can't do that. If we could, we would. If we could put that much oxygen in the water and watch what happens, that would certainly be the simplest case, and it's just what we started with minus what we ended with, right? That's the easy thing, but that really only works for a narrow range of oxygen demand levels. Okay, so with that, I want to talk a little bit about how BOD is going to act if you discharge wastewater into a river. Got a question?
I had a question on the last problem, but where does the 5-day BOD come in? Like, where does 5-day come in, or doesn't?
Okay, so the question is, where does the 5-day come in? Essentially, when we measure BOD, a lot of times our shorthand, when we say BOD, normally we just assume that's BOD 5.
Oh, okay.
We're going to talk about in just a moment a couple cases where then we might want to calculate BOD after 3 days or 8 days or something like that, how much is remaining in the system. So we will get to some of that, and that does apply essentially to our first order math kind of systems. But the sort of the generic test for BOD is a 5-day test. And so normally we wait 5 days and measure. And that's just kind of the standard way.
Okay, cool.
Good question. Okay, so when we think about a river or a stream, if it's flowing relatively constantly, essentially this is going to be like a plug flow reactor. And what we're really could be interested in, and we do this in our water and wastewater treatment class, is really take a close look at what happens when you discharge waste into it. We're not going to go all the way to the same depth we do in my other class, because that we're talking about adding oxygen into it, the re-aeration rate, and that's going to depend on how much oxygen is out of it and all of that. What I want you guys to recognize, though, is what's important is once these two mix and we have river water plus this wastewater, then we care about what happens downstream from that point and how bad is it going to get. And so if we track the dissolved oxygen over time, it turns out that given these dynamics, we may have some saturation level. We'll call that DOS for saturation. Well, we probably start before we even mix with a little bit of a deficit. So there's not quite as much oxygen as there could be because there's some biological processes. And then with this wastewater entering right here, then typically we'll have the dissolved oxygen sag down lower and eventually come back upward. So this is the characteristic dissolved oxygen sag curve. And this is going to happen at some time since the discharge or some distance since the discharge. And we may be, in terms of regulatory frameworks, we're probably interested in this point where, okay, how much is the lowest possible amount that's there? I'm going to leave it kind of at that high level. That's why we're interested. That's kind of one of the concepts that we build towards with the next bit of math here, even if we don't quite go all that way. Okay, and at the same time we have that dissolved oxygen sagging and then essentially re-aerating, right? Because it's BOD is pulling it down, so the oxygen demand is dragging the oxygen down, and then we're going to have re-aeration pushing oxygen back upwards. And essentially the re-aeration is just going to be happening. It's a physical process. The BOD is going to depend on how much food is in there. So if we can take measurements of total organic carbon, this ties in pretty well to the chemical oxygen demand, that chemical method of oxidizing stuff to see how much oxygen it will demand. It's a similar process, and then we observe how much carbon dioxide comes out. It's as a measure of substrate concentration. So how much food, how much microbe food we've got. So it's just another decent estimation, and if we track that after a wastewater discharge, it's going to look something like this, where we've got a bit of an exponential decay as the microbes are eating it. So we could take a look at the food decreasing over time, and that's going to relate to that oxygen demand. And of course, that would also relate to microbial growth if we wanted to consider. Could look like this, although in a stream type system that maybe doesn't apply quite as well, because the microbes will be stuck all over the rocks and things. So it's not like it's traveling with it. So that's not quite the in a batch case that would work, but not quite for the river type scenario. So we'll just think about the substrate decreasing over time in relation to the oxygen sagging, and then eventually the reaeration is happening faster than the BOD is being removed. Okay. Now, if we had just a batch system, that microbe growth, and we'll probably do a problem like that at some point, is that type of dynamic would make sense to look at it that way. Okay, any questions, issues? All right, so then I just want to go over a few more equations here, and that's really to kind of predict or determine how much of the oxygen demanding substances are remaining at some time. So if we want to know that value, how much BOD is remaining, let's say we do a 5-day BOD test. Well, how much is remaining that could continue to degrade or to be demanded 10 days later? That we could ask that question. After 5 days, how much is left? And it turns out 5 days gets a reasonable amount of it typically, which is why we use 5 days. It's handy. But if we think about it, there could be more. And so we can define LT as how much is remaining in the system at some time. And then L naught would be how much is remaining at time 0, which is all the possible biodegradable related oxygen demand. So this is essentially, this BOD, the ultimate BOD is essentially if we did a BOD bottle and left it incubating for an infinite amount of time, and then checked the dissolved oxygen after that. So what that means is that's kind of the most oxygen that will ever be demanded by the biological process. Okay, so this term gets a little, can get a little confusing at times because, when we do a 5-day BOD test, it's like, oh, there was this amount in that 5 days, but we have to subtract that from the ultimate amount of BOD in order to get our amount of BOD remaining, which is LT. So LT is that BOD remaining. So don't treat this as if it's equal to BOD at time t. That's not it. It's the BOD that's still remaining at time t. So keep that in mind. Okay, and we can describe that as a first order rate. So we have dLT dt equals negative k times LT. So the BOD remaining is removed with some rate constant over time, and of course then we can derive an equation for that. LT is equal to L naught times e to the minus kt, as we've done quite a few times in this class. Okay, now if we're considering the ultimate here, one way to describe this, we can say BOD at time t here. So the amount remaining, the total amount that there ever was, the ultimate BOD, is equal to the amount remaining at time t plus the amount that was already demanded at time t. So just to be very clear here, I'm going to say this is remaining versus right here has already been demanded. And that'll make sense when you think about the fact that we do these BOD tests and we measured it before, and then we measured it after, and we conclude that, oh, this much oxygen has been demanded from the system. That means that correlates to some amount of organic material. Okay, does that make sense? All right, so then we can use kind of this equation, or the combination of these two, to deal with different types of systems, whether that's a batch reactor or maybe a river that's acting like a plug flow reactor. And if we do take a river, then we're also probably having a system where we have a wastewater flow and a river flow, or something like that. And then the L naught essentially is going to be the total amount of BOD of the two combined right after they combine, right? So that's going to be the situation. Okay, and here's just a kind of a depiction, in case you're curious, of the rate at which oxygen is being removed. So a high rate of removal means we are demanding oxygen really fast, but that decreases over time because we have less microbe food, so there's less BOD, it's first order, so that means when we have not much food, there's not much oxygen being demanded. Whereas the rate of reaeration is low at first, but increases as the oxygen deficit increases. And we'll talk about when you take 3110, if you take it with me, then we'll talk about kind of how to find this point and a little more about some implications there. Okay, so on to some practice problems. So here we have dilution factor P for an unseeded mixture of water is 0.03. The DO of the mixture is initially 9 milligrams per liter. After 5 days, it has dropped to 3 milligrams per liter. The reaction rate constant K has been found to be 0.22 per day. So 3 parts here. A, what is the 5-day BOD of the water? B, what is the ultimate carbonaceous BOD? And C, what would be the remaining oxygen demand after 5 days? So starting with A, what's the 5-day BOD? let's see if we can make some sense of this problem then. Okay, so part A, we have what is the 5-day BOD for the water. This is fairly straightforward. We essentially need DO initial minus DO final divided by the dilution factor. So this is going to be our 9.0 minus 3.0 divided by 0.03. And when we do that, we should get 200 milligrams per liter.
So we don't multiply by the.
So the 1 minus p and that entire equation, which is a good question, that comes from when we have seeded dilution water. So where we left off last time, we were talking about when we have to add bacterial seed, which brings its own BOD into the water. So that specifically is for when we have to do the 2 tests. And this problem said, and this is great that you noticed that and had a question here, but this is really where that unseeded water comes into play. So we're not adding any extra bacteria and therefore BOD. So it becomes a lot simpler that way. And we didn't talk about that today, so it totally makes sense that, yeah, and the other frame of mind. Okay, so for the next problem, we're trying to solve for that ultimate BOD. We have that 5-day BOD, so BOD 5. We know that's 200 milligrams per liter. So one thing we can say to ourselves from the get-go is it should be somewhere higher than that, right? If that 5 days we removed 200 milligrams per liter, then we ultimately will remove more than that if we give it more than 5 days. Okay, so let's take a quick look here. We have 2 equations that might be useful. LT equals L naught times e to the minus KT. And then, of course, the ultimate is equal to LT plus BOD. So got this one, and we've got LT equal to L naught times e to the negative KT. All right, and so we have some information about BOD 5 here. For now, I'm just going to write that as T. So I think we need to combine the 2 and do a substitution here because we don't have any way to know so far what the ratio of LT to L naught is. We weren't given any information about really either of those, but we can relate them both to the BOD at some time. So we could say, for example, since we know this one's 200, we can say L naught equals L at 5 plus 200. Okay, so we know that much. And we could put this LT as L5 and say L5 is equal to L naught, because that's not going to change, times e to the minus k times 5, right? So we know L5 in both cases, and now we have 2 terms with L5 in it. So with that, we should be able to substitute and put one in terms of the other, and then solve for L naught. Okay, so let's go ahead and take this expression. So L naught equals L5 plus 200. And we'll check on how this compares with the book in a moment. So I have the book solutions that I'm using here. So we have that. And what we can do is say L naught is going to be equal to, if we sub in here, this will be L naught times e to the negative k times 5, and we still have the plus 200 milligrams per liter. And so now we need to get the L's together, so we'll get L naught minus L naught e to the negative k 5k equals 200 milligrams per liter. And I'm going to restart that here. So we can factor out the L naught to say 1 minus e to the negative k times 5 is equal to 200. I'm sorry for the mess here. Let me put some boundaries here. Okay, with that, then we can say L naught is equal to the 200 milligrams per liter divided by this 1 minus e to the negative 5 times k. And assuming k is in per days, which it is, and the 5 days there, I think the units are fine, and then we can solve. And it turns out if we do this, L naught should be 300. Does that make sense? Okay, so that would be the answer to part B. And part C says, what would be the remaining oxygen demand after 5 days? Well, we actually sort of solved that by doing this in a sense. We never explicitly solved for L5, but part C is going to, we'll make use of this equation here. So LT, so that's the amount remaining at time t, we can say that's going to be L naught minus the BOD at time t. So we can say L at 5 is going to be equal to 300 minus 200. So 100 milligrams per liter. Does that make sense? All right, cool. And yeah, the book gives this answer, and this rearranging business here that it's talking about is specifically referring to substituting one into the other there. All right. I think that's all I've got for you. Yes.
Are these formulas going to be given to us?
Yes, I will give you these formulas. I'll post the formula sheet soon.
I just have a question about the final. So is it cumulative or?
Yeah, it's cumulative in part because the syllabus says it in one place. So, and I do apologize. In one place, the syllabus says it's not very cumulative or something, and then at the end it says comprehensive final exam. In essence, these systems are building on each other. We started with just working with units and then with mass balances, and now we're just sort of applying it to bigger systems. So it will be cumulative in that sense. I'll try to keep the content more focused on what's recent and what you've been doing, but I do expect that the concepts are building together. Let's see. I'm going to try not to go too heavily into chemistry, for example, but maybe there will be a problem that involves a little bit of chemistry, equilibrium type stuff, especially if it's in the context of maybe oxygen demand in water and doing, some analysis on, I don't know, a bottle of water that has some bacteria growing in it, for example. I might do something like that where it's, there's a little bit of that there, but it's not the majority of the exam.
Okay, cool.
How long is the exam gonna be?
It'll probably be approximately like our normal exams, maybe one additional question type of thing. All right. If there's no other questions, I'll see you guys on Thursday. Have a good day. Wish you well on all the assignments and everything due this week.